Welcome back. In this lecture, we will continue our discussion on prompt engineering. So here are the objectives. All right, so earlier we described zero-shot and few-shot prompting, and we have two examples. The first one we have as input saying, I was XYZ with the test results, and we asked the LLM to classify the sentiment as positive, negative, or neutral. It says neutral, likely because there is no context of what XYZ means. In the second example, we added a few examples of XYZ being used in context. And so as a result, the model was successfully able to conclude that the sentiment was negative on the input. So why does this work? Well, the samples, they are really adding more context to the model. They're adding a bunch of text at the beginning that's building up on the relationships that are expected to see in the output. And then if you recall in earlier lectures, we discussed how these large language models are essentially next word generators, but they're doing so probabilistically. And we could think of this initial context as adjusting that probability of what word gets predicted next. And so let's revisit an earlier example we showed on the relationship between the input and output of a large language model. The dependency structure is unidirectional because we're following a decoder architecture. And so we see like the word dog, it depends on predicting that word both on the initial token and the current token, which is my. So basically, knowing that the sentence began with the word my, the next word is going to be dog. Now, building on that, let's look at the probability distribution of these words. And I just made these up to illustrate the example. So let's say, for example, that the model picks that with a probability of 25%. It could have picked the, maybe with a higher probability. Now, knowing that that was how the first word was picked, we are now picking the word dog, which is we're looking at the probability of the next word, but notice the first time, we were conditioning on only the start character. So here we could think of as, in this simple example, as a big probability distribution over all words you'd commonly start a sentence with. Here, we're looking at condition on two things, the start token and the word my. Building further, now that we know dog, we can condition the next word. And you're probably going to see in a sentence like this that the PDF of words at this point, because the first word is my, the second word is dog, it's likely the third word is going to be some kind of verb, just as the second word was very likely to be some kind of noun. But that is simply because it's conditioned on a different set of words than the second word was. And so we see this as it goes through, we have these probability distributions. Now, there's kind of two things to note here is this conditional here that we have been talking a lot about. If I add a bunch of extra text at the prompt, I'm changing what that conditional probability is conditioned on. So that's why having these extra examples are such an effective way in doing few-shot learning. On top of that, notice that we have a probability distribution over the word that gets picked next. Later in the lecture, we'll also discuss ways to modify how the language model selects from that probability distribution. And that's what we got here. So temperature. So when the model selects a word, it's selecting probabilistically. So if the word is going, whether that first word is going to be my or the, it's flipping a weighted coin to pick between them. So if it was the word A with a probability of 0.25, my with a probability of 0.25, and the with a probability of 0.5, it's going to pick one of those three based on those associated probabilities. Now, if we adjust the temperature, if it's a low temperature, this makes it more likely that those high probability words will get picked, and there's going to be less randomness in the result. If you pick a higher temperature, it's going to increase the probability of words that don't have such a high value being picked. There's also parameters dealing with top K sampling, so this is just limiting the top K words. So you could imagine in the slide I just showed you, you're essentially doing top 3 sampling. We're only limiting the probability distribution to having only 3 things. You can also limit the sampling based on the sum of the probabilities of the top elements as an alternative, and that's called top P sampling. But all 3 of these settings, they are available in most of the major large language models provided by vendors. Now, we talked about different types of prompts earlier on, and we talked about how few-shot learning can really help us with some of our issues. But there is a type of question called reasoning where you have to think through something, think through the result. And you have to understand, as human beings, when we get a question, we reason through the results. We think of things generally in a step-by-step way and have some kind of logic. The large language models, they don't do that. They are mimicking. They are returning an answer based on the series of words only, and they are just predicting what the next word is going to be. There is no underlying logic to that. And so for very simple tasks, such as some of the ones we've had in the slide that are very kind of, surface-oriented, a small number of sentences and stuff like that, we can get really excellent results that make this thing seem like it's very smart. But tasks that it normally fails with are where you start giving it stuff like logical puzzles or things that require step-by-step thinking. Now, in some of our own research here at ASU, we've actually seen this in practice. So what we did was we fed the large language model, ChatGPT in particular, 1,000 math word problems, and we looked at which ones it failed on, and we noticed that when the number of addition and subtraction operations required to solve the word problem increased, the probability of failure increased with that in a very direct relationship, as you see here in the slide. And when you think about an algebra problem, when you take multiple steps in solving that problem, addition and subtraction operations, that's one of the places where your steps tend to get divided up. And this is where failure occurs. So, large language models have trouble reasoning. How can we work around this? Well, one is maybe just avoid multi-step reasoning problems altogether. So if you think about the problem that you're trying to address with a large language model, is it something like a classification problem where you can get a pretty good result just by investigating the input and sort of stamp a label on it? Or does it need you to think through things step by step like a puzzle? If it's the latter, you're probably entering into the world of reasoning. So one easy fix that is surprisingly effective is adding the words, "let's think step by step," to the prompt. And this forces the large language model to kind of describe its output in a step-by-step approach, essentially creating more context for the next step, which will improve the accuracy of the result. And we saw dramatic results in the experiments we had on the last slide when we forced the large language model to show its work on a math problem as opposed to just giving the final answer. Using few-shot learning, where you have similar reasoning problems, has also been shown to help. And this is often called a chain of thought prompting, particularly where the examples have a walkthrough of the solution, where that step-by-step nature is actually in the examples. Another variant of this is to then pick examples where the line of reasoning is different among the examples. And this has also been shown to help with results. Finally, probably one of the best ways to work around the reasoning limitations of a large language model is to just have the large language model generate some kind of code or reformat the input, so then you could send it to something else that can solve the problem. And an example of this would be there was a plugin released by a company called Wolfram Alpha, where ChatGPT would take the input that was in natural language and transform it into something structural that would then be used to actually solve the problem by leveraging stuff in Wolfram Alpha's database or use Wolfram Alpha's ability to solve math problems. And so everything that involved reasoning was offloaded to this other piece of software. And you don't have to use Wolfram Alpha to accomplish this. For things like math problems, there's a package called SymPy that can solve math problems. So you can convert the ChatGPT output, use that to send off to something like SymPy. ChatGPT is also very good at automatic code generation. So if you use your textual input to kind of then structure how to solve that problem with a piece of code, maybe then that code can run and actually solve the problem. So this is another way of thinking about these reasoning problems. But the key insight here is that it's really important to recognize that when you're entering into this world of reasoning, because results get much, much worse than in other use cases for the LLM. So other trends in prompt engineering that we've noticed that are interesting. So one is that if in certain use cases where you might want to generate data for training a supervised model, like not using ChatGPT at all, or an LLM rather, is to use the LLM to just make up a set of training data. And it can do this fairly well for a lot of textual tasks. So that's actually a really nice thing. And likewise, you can use this to generate unlabeled data, which is probably will do even better because most of what it's going to produce is going to still have good grammar and spelling and stuff like that. Automatic code generation, this is an emerging use case that there's been a lot of success with, particularly with very small coding requirements. Asking the large language model itself to generate a prompt to answer a question has also been shown to be effective. And then have the model generate knowledge to use as context for the prompt. And we kind of saw examples like this when we talked about reasoning, where saying walk through step by step, that's kind of going down this road of generating knowledge to be used in the prompt. You could think of, in a session with a large language model, asking it questions about a certain period of history and then using that to preface another prompt that's asking something more specific about an individual person. So for instance, if you want to learn about John Smith, and then asking that right off the bat is probably going to not lead to good results because that's a very common name, but then prefacing it in the context of history could give much better results. So that wraps up our second part on prompt engineering. Stay tuned for more content.